Hi there. This is a follow-up video to one of my older videos on Python list versus deque, where I had given a detailed insight about the implementation, about a list and a deque, and told you how they're different and so on. I apparently stumbled across one YouTube video which got my attention, which was titled as a deque being more memory efficient than a list. And I was wondering, is it really the truth? Is there any truth in it? Let's just find out right here. Well, here on my Python prompt, as you can see, I will create two data structures. One a list, another one is a deque. So let's try with a small size first and then larger sizes. So all I want to do is I'll say from collections import deque, right? And first time I will just create a list, call it a variable called a representing a list. I'll say a is equal to list of range of, let's try to create a small 10 element list, right, to begin with. I'll try to create a deque same way. I'll say d is equal to deque of range of 10. The first one being a list, the second one being a deque. You can see of the same size, right? But what is the memory footprint of both of these data structures? To find out the memory footprint of any Python data structure or object in general, you could actually take help of this module. The sys module in Python provides a function called getSizeOf, which will tell you the overall memory footprint of a given Python object. So if we say sys.getSizeOf a, you can see that it takes up 136 bytes of memory. What about sys.getSizeOf d? Well, quite large, right? It's many folds bigger than a list. But remember, this is a smaller sized list and a deque, but as you increase the size, you'll not see that difference too high, but still you'll see some sizable memory usage of a deque compared to a list. Here's let's try to create a list and a deque with 10 million elements this time, right? So I'm just going to say a is equal to list of range of 1 followed by 1 0 followed by 3 zeros 3 zeros. So this makes it 10 million, right? This is a 10 million element list. I'm going to create a deque of the same size by d is equal to deque of range of 10 million. And now you can see that there are two very large, it's quite large enough size list and a deque. Now I want to find out whether the size difference really matter in this case. So if I try to say sys.getSizeOf a this time, you can see it roughly takes about 80 megabytes. It's like 3 zeros, another 3 zeros. It's about roughly 80 megabytes for a list. 80056. The 56 is the extra metadata overhead, right? But we try this for a deque. It's actually 82 megabytes. It does take up more memory than a list. So a deque is not memory efficient than a list. Just note this. Also, coupled with the fact I told you in the previous video that a list is backed by a vector, which is a dynamically growing array. It's an array of pointers ultimately, right? So the 0th index of the list data structure internally will have a pointer to the item. The first index will have another pointer to the item. All these pointers are in a memory contiguous array, which also means that they are more cache friendly. Which means that when you try to get a particular element of a list, you can easily get the neighboring elements without doing complex memory hops. So it might be very hot on the cache line already, right? A deque, on the contrary, is not like that. A deque is not backed by an array. As I told you, it's backed by a circular, doubly linked list. Which also means that each node in the linked list is not guaranteed to be memory contiguous to another node. They might be scattered across on heap. And due to this nature, if I try to get one item from a deque, through one of the nodes, if I want to get to the neighboring node, it's a memory hop, which may not always be cache friendly. So there will be some of these performance implications because of that nature. Though this might not be very highly visible, right? It might depend on the CPU architecture and many other aspects too. But here's something you should keep in mind. So a deque is not some magic data structure which is going to be super efficient than a list. A deque is good at only one thing. You can add at the either ends of a deque with minimal complexity, right? You can add in the beginning, remove from the beginning, add at the end, remove at the end. And some of you might ask, how much of difference does it make to add or remove elements on either side of a list or a deck, right? So to demonstrate that, here's another example I'll show you. Here's, okay, let's take this 10 million element list itself. So let's say I want to keep adding an item in the beginning or removing an item in the beginning. I want to see what's the performance implication for that. So what I'm going to do is I'm just going to say a dot insert at the 0th index some random number, let's say 67, some number, doesn't matter, right? And I also remove it. I'll say a dot pop of 0. This is how we remove from the beginning. Add an item, remove an item. I want to find out the time complexity of this, performance complexity of this. For this, you can use a magic command on IPython and Jupyter Notebook, which is %timeit. It is built on top of the timeit module. It reduces the boilerplate. It's very easy. Just say %timeit and put any statement or any expression. It's going to execute the statement expression multiple times and give you a more fair enough, accurate average time taken for performing this operation. It will take some time for this to compute. Let's wait. By the way, this A is representation of a list. Okay, so I'm trying to run a list. So it's going to take some time. Yeah, it took about 14.5 milliseconds plus or minus 49.5 microseconds per loop by running this 7 into 100 loops. So mostly like 700 times it executed it and found the standard deviation of it and the average from there, right? I'll try the same thing on a deck. For a deck, you don't use insert, you say append left and pop left to add or remove from the beginning, right? Let's say d dot append left, or I'll just try using 67, and I'll say d dot pop left to remove from the beginning. And let's find out how much time it takes. You see here, this is what a deck is good at. You can see that it's able to do the same operation in just about few nanoseconds. And this is the truest power of a deck compared to a list, adding or removing elements at the beginning, right? Apart from the end. Another aspect I shall tell you where deck is slow is random access. So here I have anyway 10 million element list and 10 million element deck. So I'm going to show you something. I want to find out how much time does it take to access an element at 4 millionth index or maybe 3 millionth index, right, to begin with. So I'll just say %timeit a of 3 million. The 10 million element list, so I'm accessing at this particular index. It's just going to access that index and multiple times and find out the time taken. We're all on a list. 25.9 nanosecond plus or minus 149.149 nanosecond per loop, right? Try the same thing with the deck. Do you see the performance difference here? 520 microseconds. And this is the reason why the default built-in data structure in Python list is backed by vector, because vectors are optimal for random access. In fact, it could be 3 millionth element, or I could access even the 5 millionth element, which is exactly towards the half the size, right? Half the size of the list. You can see that. I'll try with the list first. 5 millionth index. 10 million elements. It's almost the same time. See, there's hardly any noticeable difference. It's 25.6 nanoseconds plus or minus, right? So it's almost 01 no matter what index you try to access in a list. But when you try the same thing for a deck, it's going to be a little different. Trying to access the midpoint of a deck is very slow. You can see that it's 2.44 milliseconds. So what you'll see here is a deck is inefficient at random access. Indexing elements in a deck can be very expensive. It's most expensive, I realized, at the midpoint of a deck. Somehow I realized that if I try to increase to the next index, which is like 6 million index, it'll not be slower, it's slightly faster. Because the way the indexing works, right? So they are managed to do it's circular linked list, so it can traverse in both directions from left to right. You can see it's reduced to 1 millisecond. If you go to, let's say, not 6, but let's say 7 millionth element, it will be even more faster. So if you go towards the end, it'll taper off. Go towards the beginning, it'll taper off, but it'll be taking the maximum amount of time towards a midpoint of a deck. You can see here, obviously. So there are things you keep in mind. To summarize, a deck is not memory efficient than a list. It does take up more memory than a list. A deck is very inefficient for random access, which we see right here. But what is a deck good at? Adding an item in the beginning or removing an item from the beginning. That's it. And yes, you can also rotate a deck. As I told you, rotation is cheap. You can make the first element last or last element first, depending on what kind of rotation you do, whether you do clockwise or anti-clockwise rotate or rotate of -1. Any of these options, they are quite faster on a deck. That's about it. So for every other purpose, if you're looking at random access kind of an array like functionality, I think you should stick to a list, right? And list is memory efficient than. Hope this clarifies some of the misconceptions that you might have. Hopefully you found this video useful. Hope to meet you in another one. Thank you.